Hi, I'm Quinn, and today we're unpacking reversibility of quantum computing. Quantum computing has a strict rule: no information loss. That's because quantum gates are unitary and unitary operations are reversible. If you know the final state in the gates, you can always run the computation backward. Classical computers don't follow this rule. Gates like AND or throw away information. Multiple inputs map to the same output. Once that happens, you can't recover the original inputs. That's irreversibility. Classical computing is like breaking eggs to make an omelet. Once you've cracked those eggs and scrambled them, there's no way to get the original whole eggs back. Information is lost, you can't uncompute your way backward. Quantum computing is fundamentally different. It's like watching a synchronized swimming routine. Every move is precisely coordinated, and if you filmed it and played the video backward, you'd see another perfectly valid routine. The swimmers could retrace every twist, turn, and formation back to their starting positions without losing any information about the path they took. This is quantum reversibility. Every quantum operation, except measurement, can be run backward. The mathematical transformations are what we call unitary. They preserve all information and can be perfectly undone. Just like how a video running backward only works if nothing random happens. Imagine trying to reverse a video of eggs breaking. Impossible. Quantum operations maintain this perfect reversibility by keeping the quantum state in a controlled, deterministic evolution. The moment you measure the quantum state, though, it's like those eggs breaking. You collapse the superposition and lose that reversibility. This reversibility is both a powerful feature. It lets quantum algorithms explore solution spaces in sophisticated ways. And a constraint: quantum programmers must carefully manage uncomputation to avoid accumulating garbage qubits. Why does it matter? There's a deep physical principle here called Landauer's principle, which says erasing information has a real energy cost. Reversible computation in theory avoids that cost. In classical, irreversible computing, when you erase a bit, it's like having a car drive off a cliff into the ocean. That car is gone, you've destroyed information. Landauer discovered something remarkable. Pushing that car off the cliff always costs energy and generates heat. No matter how clever your cliff design, gravity demands its price. This minimum energy cost is about 3 times 10 superscript 2 superscript 1 joules per bit at room temperature. This is why your laptop gets hot, billions of bits being thrown off cliffs every second. In reversible computing, you never throw cars away. Instead, you shuffle them around the garage. You might move car A to spot B and car B to spot A. No cars disappear, so no energy is fundamentally lost to heat. So how do we do classical logic in a reversible world? We use reversible gates like Toffoli. The Toffoli gate takes 2 control bits and flips a target bit only if both controls are 1. It can compute and without destroying the original inputs. That makes it reversible, and it's enough to build any classical computation. In quantum algorithms, measurement is the boundary where reversibility ends. Measurement collapses the state and produces a classical bit. That step is irreversible, which is why most algorithms delay measurement until the very end. The takeaway: quantum computing is reversible by necessity. It's not just a design choice, it's a fundamental requirement of the physics. Quantum operations must be reversible because they are unitary. On the other hand, classical irreversible gates discard information which quantum evolution forbids. Reversible gates like Toffoli can simulate classical logic without loss. Measurement is the only irreversible step in a quantum algorithm. That's all for today. Take care.